Okay, so in this video, we are going to look at a Moore machine. Okay, so we have already seen this term when we studied the classification of FAs. So while we studied the classification of FAs, we said that there are two categories. One is without output, without without any output, and the other classification is without. Okay, so Moore machine is an FA which is having an output. So there are two, in fact, there are two machines. One is a Moore machine, and the other one is a Mealy machine. Okay, so we'll study about both of this. We'll start with Moore machine. Remember, the category, without output, in the category of without output, we have all these varieties like DFAs, NFAs, what else, epsilon NFAs. So all these comes under the category of without output. So this is very important. So we are going to look at we are going to focus on this portion now. Especially in this video, we are going to look at Moore machines in particular. So the peculiarity of one of the peculiarities of Moore machine is that it can generate an output. So it will generate an output. This is very important. So this property was not there with DFA, NFA, or epsilon NFA. So in DFA, NFA, and epsilon NFA, the idea of acceptance of a string was there. Okay. So in Moore machine, there is no such concept of accepting a string or string. Okay. So the idea here is that what is the kind of output that it generates. So this is going to have importance here. So in NFA, DFA, and epsilon NFA, most of the time when we looked at, we are looking at what kind of strings it could accept, and therefore what is the language represented by this FA. That was the key point that we are looking into. Now in Moore machine and also in Mealy machine, we are going to look at how it is generating the output. Okay, and how can we customize the output which is getting generated. So that's going to be our focus. Now, and again, one more very important thing here with regard to Moore machine is that there are no final states in a Moore machine. No final states. Okay, so these are very important. So there are no final states, and this generates an output which is very important. There are no final states, and just to mention, there is no concept of string acceptance. Okay, so we are not using Moore machine or Mealy machine for the concept of string acceptance. Rather, we are looking at generating output strings. Okay. So with this brief introduction, let's look at an example of a Moore machine. Okay, now when you look at this diagram, this is just an FA. Okay, this can be considered as an FA. So we are going to convert this as a Moore machine. Okay, so what essentially is required for a Moore machine is that every state in a Moore machine has to be associated with a particular output. So for example, state Q0 is associated with output X. Let's say let's make it very general. So again, Q1 is also has to be associated with an output. Say I'm just saying Y. Okay. So remember, every state has to be associated with a particular output here. Okay. Now let us try to understand how Moore machine handles a given string. So suppose that the input string is, say, BAB. BAB is the input string. Okay, and again, remember that here the alphabet set is A, B. So you can have strings which contain A and B. Okay, so suppose that our input string is BAB, then we are going to look at how this BAB is processed by the Moore machine and how it generates the output. Okay, so remember, don't forget to mark the starting state here. So in a Moore machine, whenever you start processing, even before you start processing a string, you are already in the starting state. Okay, so if you look at here, you are already at Q0 even before starting to process your input string. So since you are already at Q0, you definitely will have X as one of the output, because X is an output which is generated by the starting state. So even before you start to process your string, so your output, let me make it very clear, your output. So I'm going to write the outputs here. Okay, so your output will contain X. Okay, now what happens once this machine processes B? So B is the first symbol in, or the first character in our string. Okay, so when it sees a B, so the shift is from Q0 to Q1. Now we can see that the output available at Q1 is Y. So this also gets added up to our output. Okay, so Y becomes a part of our output now. Okay, so we have processed B. Now we are processing A. So when you find an A from Q1, A from Q1. Okay, so when you find an A from Q1, it goes to itself. Okay, so you can see that A from Q1 goes to itself. So again, you will get an output of Y. Okay, so let me write Y again. Okay, so we have processed B and A. Now we are left with one more B. So when you process that B from Q1, okay, from Q1, if you process that B, what happens? So you'll be reaching back to Q0, and remember the output symbol available at Q0 is X. So that X will also get added to our output. Okay, so let me add that output to our set of outputs. So this becomes X. So that's the end of the string, and finally we got the output string as XY is YX. Okay, so this is going to be our final output that we got from this Moore machine. Okay, so in this way you can be given with any Moore machine. Remember that that in a Moore machine the outputs are indicated inside the state itself. Okay, so this is very important. Whereas in Mealy machine the output is represented along with the transitions that we will see later. But remember, very importantly, in a Moore machine, the output is associated with the state itself. So if you look at every state, okay, there will be a corresponding output associated with that. Okay, so that's very important. Now, one more very important thing here is that if you notice, our input string contains only 3 characters, whereas our output will contain 4 characters. This is because of the fact that the output in the starting state will be coming to our output. Okay, so this is a default output. Okay, so a Moore machine always produces a default output, that is the output present in the starting state. So this X will be, by default, it will be available in our in our total output. So whenever you perform transitions, okay, since there are three characters, B, A, and B, for all these 3 characters we will get some other output. So for the first B transition we got this Y as the output. For the A transition we got this Y again as the output. For the last B we got X as the output. So the idea here is that if you have n elements in your string, okay, so if you have n elements in your string, then you will have n plus 1 n plus 1 characters in your output. So n characters in your string will mean n plus 1 characters in your output. So this is also very important. Again, we have a very interesting situation. What if our input symbol is just an epsilon? Suppose that our input symbol is just an epsilon. Okay, so what will be the output? So this is going to be very interesting. So remember, even if your string is epsilon means it's an empty string, right? So so even if you have nothing in your input, so you are already at Q0, which is the starting state. So even if your input symbol is epsilon, you will have in this case you will have X as the output, because X is the output that you're getting from the starting state. So remember, you are always starting from the starting state, right? So you don't require any non-empty string to be there in the starting state. Okay, so even if your input is an epsilon, your output, okay, so let me write it very clearly. So if your input string is epsilon, still you have an output. Okay, so your output is going to be X in this case. Okay, so this is very important. For even if your input string is an empty string, you will still have the output that is available in the starting state. Now, before actually going into the mathematical definition of a Moore machine, let's look at some very simple problems which can be solved by a Moore machine. So in this question, we are asked to design a Moore machine which will count the number of A's in the input string. Okay, so where the alphabet set is A, B. So if the input string is A, B, B, A, then our Moore machine should be able to count the number of A's. Now in this string there are 3 A's. Okay, so our Moore machine should produce an output by looking at which we will be able to identify that there are 3 A's in our input. Okay, so this may not be directly relevant, okay, by looking at the output, but in some sense we should be able to make it out that there are 3 A's in the given input. So let's design it and then it will become more clear. Okay, so what we are going to do here is let's start at, say, Q0. Let's start at Q0, the starting state. Okay, so what we are interested in is to count the number of A's. Okay, so it means if you are seeing B's, you are not going to count anything. You just want a 0 output there. Okay, so as long as you see B's, your output is going to be 0. Now if you see an A, then you have to count that. Okay, so whenever you see an A, you are going to output 1. Okay, so this is very important. Now again if you see an A, you have to stay in that state itself, because you have to count it again. You have to increment that count. So your binary output should represent that. Okay, so in fact it is not a binary output. Okay, so we'll come to know it later. So if you are getting again an A, you have to come back to Q1, and again the output should be 1. From here, if you are getting a B, since we are not interested in counting B's, it has to go to Q0 where the output is 0. Okay, so this is our answer. Okay, look at this. There are no final states. There is no concept of a final state here. The only concept here is that if you give this kind of a string A, B, B, A, so our output, the output given by the Moore machine, will indicate a value of 3. Let's understand how it does this. Okay, so let's process this string. Let's process the string using this Moore machine. Okay, so initially you're at Q0, so by default you will have an output of 0. So let's write the outputs also parallel. Okay, so for writing the outputs, okay, so I'm going to write the outputs here. Okay, so let me make it very clear. Let me write output. Okay, so I'm going to indicate the outputs here. Okay, so initially, without doing anything, we know that this 0 will be present in our output. Okay, so once the string is getting parsed, okay, so this first character that we see here, very first character that we see here is A. So So since you are getting an A, your output now will be the output present at Q1. So that is 1. So our output will be, our output will contain this one. Now the second character you see is a B. Okay, by looking at here. So the first character we have passed. We are now looking at the second character. It's a B. So we are now at Q1. From Q1, when you are getting a B, your output is going to be 0. Okay, so let's write that output here. Okay, now we have to again. Now we have finished A, B, and then again we are meeting with a B. Okay, so we are at Q0 now. When you see a B again, your output will be again 0. This 0 will be coming to our output. Okay, so let me write that 0. Okay, so our output will again have a 0 there. Okay, now that we have finished till A, B, B. Okay, now we are left with 2 more A's. What will happen now? So whenever you see an A from Q0, you will be at Q1 and it will output again a 1. Okay, so you get a 1 here. Again your string has 1 more A. Okay, so you'll get a transition like this back to Q1. Again, you'll get an output 1 here. Okay, so this particular output is a clear indication that our string contains 3 A's. Okay, so whenever we got an A, we have marked it as a 1. Okay, so if you count the number of ones here, okay, so if you count the number of ones here, then it is going to be 3, and that's our answer. So this is a very ingenious way of designing a Moore machine, which will actually have a way of counting the number of A's in the input string. Okay, so if you are asked to count the number of B's in the input string, this is going to be very easy. The only thing that you need to do here is that you have to switch between, you have to replace all B's with A's and all A's with B's. Okay, so this example is a clear indication of how we can use Moore machine to generate useful outputs. Okay, so in this example itself, we have generated this output from which we can actually derive the number of ones in the given string. Okay, so these kinds of very interesting problems can be solved using Moore machine. Remember, all such problems demands some output. Okay. Now, based on these outputs, we can actually derive very interesting features. Okay, so in our next video, we will define, we will have a look at the mathematical definition of a Moore machine, and then probably we'll look at few more problems.